Welcome back to ECE 442-542. We are working some problems, and these problems are being worked to prepare you for the second attempt on quiz number 6. These are actually problems that you were working for the first attempt on quiz number 6, and let's now go through some of those in essentially the most challenging problems to the least challenging problems. And the first one probably shouldn't have been a challenging problem, but maybe it threw you because I said the phase angle is approximately. But I'm wanting you now to really pull out your engineering tablet and have maybe this unit circle or z-plane ready, and you can now have a protractor and immediately sort of compute the angles that you need to work through some of these problems. For example, here you're asked for the phase angle of this transfer function g of z. That could have been g of z, c of z, it could be any transfer function. Now you're trying to find at this point in the complex z-plane, which is j 1/2, so we're going up the imaginary axis a distance of 1/2. We want to know what's the angle of that entire transfer function g of z. But you can think about that angle in terms of the different factors that contribute to that angle. You have a zero factor. That zero is right at the origin. You have a pole at 1/2, positive 1/2, and you have a pole at positive 1. And I've labeled those angles theta sub p sub 1 because of the pole at 1. And that angle, you can see, is larger than 90 degrees. And a lot of times I will calculate the acute angle and take that away from 180 because I can quickly compute that with my calculator. Likewise for theta p sub 2. In fact, in that particular case, hopefully it's clear that you're going up vertically as far as you're going across horizontally for the acute angle, or that acute angle corresponding to theta p sub 2 is 45 degrees, so theta p sub 2 is in fact 180 minus 45, or 135 degrees. Likewise, I set this up to try to make it clean or quick for you to sort of think through these angles. Theta sub z, that's the angle of the zero, and there you're just looking straight up from the origin. Theta sub z is then 90 degrees. So if we now look at some of those, we said theta sub p sub 2 is now 180 minus, let me get the right tool. We're now looking up 0.2 and walking over 0.2 for the acute angle. And so this is in fact 45 degrees, or as I said before, theta p sub 2 is 135 degrees. Theta p1 is a little bit bigger than that. You can see that your angle is now a little bit larger for theta p1 than theta p sub 2, and you could physically measure that if you had sketched this accurately. But here we are going, and where did I get 0.2? Thinking about another problem. This is 0.5 over 0.5. I'm sorry about that. But I hope you see that the vertical distance is equal to the horizontal distance. For theta p1, you now have a vertical change of 0.5. This is then the acute angle, and we're going over a horizontal distance of 1. In fact, this angle is 26.56. We take that away from 180, and we do obtain an angle that is larger, which is what we visually saw. Theta p1 is a larger angle than theta p sub 2. We now simply algebraically combine those angles. The angle of the entire transfer function g is the sum of the zero angles. Here we simply have 1 0, theta sub z, minus the poles angles, and that's adding the zeros and subtracting the poles, that's just because the zeros are in the numerator, the poles are in the denominator. We do that algebra. We have 90 minus 135, that's minus 45 degrees. We take away from that this theta P1, which is minus 153. And if you sort of round that up to minus 155, you see that you're coming in at minus 200 degrees. Now you might have calculated that with a calculator. You could say, what's the angle of that transfer function, where the transfer function is just z over these two pole factors, and we want to evaluate that. That's now the vertical bar. We want to evaluate that angle when z is equal to I, or in the imaginary direction 0.5. If you called this up from the menu in your Inspire, that might produce then a radian value for your angle, and that kind of is explained there. So I then in the second line converted that to degrees. So that angle is now 162 degrees, and you may not have seen that on the answers, but realize that you could add and subtract 360 degrees from that angle to get another angle. Maybe I should have kept the angles between plus and minus 180, but usually I like to think in terms of negative angles, because I'm going to probably be relating those negative angles to a time delay, and that's why we now have a negative angle making us this negative time delay in the time response behavior. But that's now saying, okay, we had minus 198, that's approximately, that's what I'm saying approximately is okay. This is now approximately minus 200 degrees. Now you can see, I hope, that I could have asked you for the angle of G anywhere. I could have maybe said, oh, what's the angle of G of Z at this point? And then you would simply have to find those angles. You have theta sub Z. Now that's something a little bit less than 90 degrees. You have the angle due to the pole at 0.5, which is now going to be 90 degrees. And you have the angle from the pole, and that's now going to be a little bit smaller for theta P1 than it was in this previous example. And you could then algebraically combine those and determine the actual value of that angle. In this particular case, where we were looking at the triangle, we had an angle of minus 200 degrees. I could have asked you, is this point J0.5 on the root locus? And because the phase at that particular point in the z-plane is minus 200, it's not minus 180, you now know that the root locus is not passing through J0.5. You would need it to be closer to minus 180. It's now minus 198, so we need to not take so much angle away through the poles, or if we started to slide that point up vertically on the imaginary axis, and if we slid that point up in a manner that maybe allowed the angle of theta P2 to be about 10 degrees smaller than 135, and theta P1 about 8 degrees smaller, then we would be passing through, or we would have an angle at that cloud location of minus 180. Oh, and now that spot is on the root locus. So you could see that you could numerically evaluate any particular location. If somebody now said, oh, I want to know where the root locus intersects this dashed vertical line, you could now start looking. I mean, you wouldn't really want to do this, but this is to give you insight. You would just plot this in MATLAB to see the root locus, but now you would say, oh, the angle at this point was, let's say, minus 195. Well, now you know that you need to maybe go up here a little bit higher in order to say, oh, that diamond is now where the root locus passes that particular imaginary, or that virtual line that we drew. And then you could do a lot of those vertical lines and get these points in the complex Z-plane that have an angle of minus 180. You now connect the dots and you have your root locus. That's another way of thinking about what this root locus diagram is doing. But in this problem, I was just asking, find the angle of this ratio of polynomials in Z at a particular spot in the complex Z-plane. And you should be able to do that if I now tell you, oh, here's your spot down here. What's the angle that is being determined by this transfer function, g of z, or any other transfer function that I might ask you? That was a long-winded answer for the problem. A lot of that was not needed, but I hope that you now have better insight into that particular problem. Here, and again, all of these are assuming our standard block diagram. We have our controller, we have our plant, and that's now a negative unity output feedback. Instead of me continually trying to insert that figure into these problems, I've tried to include a sentence that describes the interconnection structure. Now we're asked, identify the real axis line segments where the root locus experiences a re-entry point. We have breakaway and re-entry points. Assume we have K for our controller and now our plant. I hope I've already indicated the poles and the zeros. We have a 0 at the origin. We have 3 poles, one at 1/4, one at 1/2, and one at 1. Now we can use Rule 2. We've used Rule 1 to locate those poles and zeros. Rule 2 now says, oh, just look for odd numbers of poles and zeros to the right of these line segments. And now those are the line segments where our root locus lives. But we know that we start on poles, so we in fact have 2 branches between 1/2 and 1 of our root locus. We have 2 branches of the root locus. We have 3 total branches of our root locus. Here's our 3rd branch, and that's staying between 1/4 and the origin. Now what happens? Well, now effectively we have a pole 0 excess. We have 3 poles and 1 0. Our pole 0 excess is 2. So in fact we have 2 zeros at infinity, and that tells us then that those zeros are splitting our complex Z-plane into 2 uniform pieces. Or this now is saying, oh, we actually have a breakaway point between 1/2 and 1, and those 2 branches go off to infinity at 180 degrees divided by 2. Now we're getting into Rule 4, but you didn't need to know that for this answer. Now it's saying, which line segments do we have a re-entry? Well, we don't have a re-entry, so hopefully I gave you the option in that problem to say none of the above if all I had indicated were the different line segments. Here's a line segment, here's a line segment, here's a line segment. I'm going to run out of colors. Here's a line segment, and we also have another line segment over here. We only have 2 of those line segments on the root locus, but even with those 2 line segments, we have 3 branches. We have 2 branches between 1/2 and 1, and 1 branch between 1/4 and 0. I hope that's now clear. So in this particular problem, you would say no segment of real axis provides a re-entry point. There is no re-entry for that problem. Assume a standard, here again is our standard configuration. If a controller is given by, this is now a PI controller, we have a 0 at 3/4, a pole at 1, and we have a pole of our plant at 1.5. This now is our familiar configuration, 2 poles to the right of 1, 0, and those are the only poles and zeros we have. If we have other additional poles and zeros, we do not have this nice circular geometry off the real axis for our root locus sketch. So this is specific for 2 poles to the right of 1, 0. We can compute, what's this question asking? It's saying what is the minimum value of gain K to achieve stability? And I've tried to indicate a unit circle. That's not anything to do with the root locus, but I hope you can see that in fact we need to crank up the gain. We have 2 branches of our root locus between 1 and 1.5. Those 2 branches split. One goes here, the other branch goes here, and then it doesn't matter which one goes where. One is going to go to the 0, the other one is going to be going zipping off to -infinity. But I hope you can see that when we crank up the gain enough to where the upper branch and the lower branch, they are symmetric, we'll have both poles finally at the same time simultaneously. We have 2 branches. We need those 2 branches to simultaneously be inside the unit circle. The first time or first value of gain that occurs is at that box. We need to crank up the gain K to get us to that location in the z-plane, which is maybe given by z box as a plus jb, and then we need to find the gain K to get us to that location. We could in fact calculate the breakaway point. The breakaway point is this geometric mean of these 2 lengths. The lengths are determined by the distance from the center of this circle to each of those pole locations. L1 is then the distance from 0.75 to 1, or that's 1/4. The second distance length, L2, is the distance from the circle's origin, which is 0.75, out to the second pole at 1.5 for a distance of 0.75. We form their product of L1 and L2 and take the square root. That's now the geometric mean. That says that our radius is 0.433. We didn't need all of this to answer this question, but I'm just giving you this because you might be asked that on the second attempt. The breakaway then occurs the radius to the right of the circle's center, which is 0.75 plus r. For r equal 0.433, that gives us a 1.18 for the breakaway, and that's between 1 and 1.5. Good, that's consistent. But notice it's not halfway between. It's not at 1.25. It's breaking away a little bit closer to the pole at 1 than the pole at 1.5. We would re-enter then inside the unit circle on the real axis a radial distance to the left of the center, or at 0.75 minus r, which is then at 0.317. We're trying to find the minimum K to get us to that box. We've cranked up the gain from 0, and we want to know, okay, how far do we crank it? We know we can't crank it up too far, or one of those poles, and that's all it takes is one pole to zip outside the unit circle. We need both branches simultaneously, and if we had 5 branches of our root locus, we would need all 5 of those branches to be simultaneously inside the unit circle to preserve stability, closed loop stability. We could find Z box, and if you sketched this out accurately, you now have your compass. You can draw these circles. Maybe you've pre-sketched a Z-plane on engineering grid paper with a unit circle. Now you sketch these poles and zeros. You put down your compass. The center of that compass is at 0.75. You know the radius is 0.433. You can draw that circle of your root locus and, in fact, graphically determine where that box is, and you could find a plus jb. Then, if you did that, you would be wanting to find the gain, which is going to be a product and ratio of these lengths, and you need to include the scaling factor if there was a gain in your numerator or denominator of C or G, and here we don't other than the factors, but we could then calculate the gain K that way. Here let me do it another way. We know that the closed loop poles are given by, because of this standard configuration, we know that we have T sub C is GC over 1 plus GC. Our closed loop dynamics are governed by that denominator expression. That expression for this particular problem was the PI controller and the plant. So that's K over this times this 0 over these two poles. We want to know when that equals 0. We're really just interested in the numerator, so we put that over a common denominator of z minus 1 and z minus 1.5. We forget the denominator and just examine this second order polynomial in z as a function of, now the only unknown besides the z's is k. And that's we're trying to find the minimum value of. Well, we can distribute or multiply all of this out, and we end up then with a quadratic. We have an unknown linear factor. It's a function of k. We have an unknown constant factor, but on the unit circle, which we know k min, that's where we first encounter the unit circle, we know that that magnitude of a plus jb is equal to 1. So we know that the quadratic z squared, etc., must have roots with magnitude of 1, and that says then that the constant term is equal to 1. So now we know 1.5 minus 3/4 k is equal to 1. Oh, we now have one equation in terms of k, and that's in fact the minimum value of k that we need. So in this case, our k box is going to be 4 times a half, that's just 2, divided by 3, or 0.67. That was really what we were asking to find, and we could have sort of quickly started here, known that we needed to get to the unit circle. That now tells us, oh, this is what's important. Solve that for k, and now we have our minimum k. A little bit extra is if we now know that k is 0.67, we can plug that k in to this quadratic and find where the roots are, and that's now z box. Z box is 0.916 plus or minus j 0.4, and you should be able to show that the magnitude of z box is equal to 1. Now we could, if we now had z box, we can use that z box in our k expression, the magnitude expression, which we find from the magnitude condition, to calculate k min at a plus jb, where a plus jb is this 0.92 plus and minus j 0.4. The magnitude condition then says the magnitude of kgc is 1. We solve that for k, and evaluating it at z box, yes, we do achieve a consistent answer. That tells us that we need to crank up the gain beyond 0.67. I could have asked for what's the maximum value of k. Then you would use this expression and evaluate it when z is equal to minus 1. And that would be your maximum value of k for stability. So there's all sorts of questions that can be asked for these kinds of problems. So if we did that, now I'm playing with fire, but let's now say, oh, we did a box, so let's now say that k triangle is when k is equal to minus 1. we now have minus 1 minus 1.5 over minus 1 over minus 1 minus 0.75. And if we compute that, do I even have that available? Let me quickly see if I can do that. And we end up with the maximum being 2.857. I usually would round down so that I don't get all the way to the unit circle or beyond. This is now our K max. Again, that wasn't asked in this question, but it could be asked on the final or in the second attempt or any other quiz time. Assume now the next question. Again, we have the normal configuration. We have a PI controller, and somebody now wants to know, where do we locate the 0 of that PI controller? That's the alpha in this z-plane plot. The pole of our plant is at 0.8. That's the blue X. We have, because it's a PI controller, we're forced with a pole at 1. That's the integral action. Now, really what we're asking is, once somebody tells us where that triangle is, we are saying, can we actually make the root locus pass through that triangle? And this is really a 2 poles to the right of a 0, but we can use the phase angle condition because we know that that triangle, all of our closed loop poles have to have an angle of minus 180 in order for those points on the complex z-plane to belong to our root locus. In this case, then, we can find, once somebody tells us the triangle, which is 0.8 plus j 0.2, and we know the pole of our plant at 0.8, we know the pole of our integrator at 1, theta p1 is then 180 minus inverse tangent of 0.2 over 0.2. Again, I kind of spec this so that it's not too hard to find. This is now 180 minus 45, or 135 degrees. Theta p sub 2, we just look straight up. Theta p sub 2 is 90 degrees. Now the only unknown in this phase angle condition expression is theta sub z. Theta sub z is now minus 180. Solving for theta sub z, we're just going to add all of those pole angles on the right, or on both sides, so that we're left with theta sub z on the left is equal to minus 180 plus 135. So now we're at minus 45 plus 90. So theta sub z is 45 degrees. We now need to find alpha such that the angle theta sub z, and here's another sketch of that. Here is an isolated picture of what we're trying to do. We now could get even out our grid paper and say, oh, from this triangle I need an angle of 45 degrees looking up from the real axis. Well, then we know that we have a vertical distance of 0.2. To get 45 degrees, we need the same distance horizontally. So now we know x is equal to 0.2. And that immediately then tells us what alpha is, because we know alpha, the 0 location, plus x, which is 0.2, needs to get us to that real axis value of 0.8. So alpha in this case is 0.6. Again, we have our standard configuration. Now we're asked which point z, and I probably gave you a list of points, which point z is on the root locus. Well, now you simply have to draw your root locus. Rule 1 is to sketch the poles and zeros, so remember, those are the values of z that cause those denominator factors to vanish. So the first one vanishes when z is equal to 2, and the second one vanishes when z is equal to minus 3. Don't get those mixed up. So we have a pole at minus 3 and a pole at 2. Now we have this infinite real axis. We're splitting it up into, cutting it up into 3 segments. One segment is determined, or one of the cuts is at 2, the other cut is at minus 3, and now we know that our root locus, and we have two branches of the root locus, lives between z equal to 2 and z equal to minus 3. We have only two poles. This now is this nice, quick, easy to draw root locus. We have a distance between those of 5, and because we only have two poles, no zeros, no other poles, we know they're going to meet halfway between each other, or we divide 5 by 2, so now the breakaway point is 2.5 units on either side of these two poles. So now we go 2.5 units, and now that's our breakaway point. One goes up and one goes down. And now, hopefully, you start saying, oh, did the question give me a pole here? Did it give me a pole here? Or did it give me a pole somewhere there? Those poles now would all be on the root locus. And in this case, I think I gave you one with a real value of minus 1/2, which in fact is on that vertical branch going up after the breakaway. So here you're looking for a 1/2 plus j, and now you could be anything. I don't know what I gave. I think maybe I spec'd it to be 0.866, but I could have said minus 1/2 plus j 100, and that would be on the root locus. But if I gave you now a value of, let's say, something over here, z equal to 2.5, you know that's not on the root locus. Likewise, any point here, -4 is not on the root locus. If I gave you a point here, that's not on the root locus. So you have to simply draw the root locus and look and compare where that's located with the points that were provided in the question. If we have this scenario, we have a pure gain controller, K, and a plant, and now I've tried to do rule 1 already. I have a pole at the origin, a pole at 1, and a pole at 2, and I have a 0 at a 0 at 1/2. Now we need to do rule 2, which is find the real axis segments that correspond to the root locus. So we start looking for real axis segments with an odd number of poles and zeros to the right. We now can see that we have two branches between 1 and 2, and we have one branch between 0 and 1/2. And the question is, how many root locus branches exist between 1 and 2? The answer is 2. We have one segment, but there's two root locus branches on that segment. And now, if you wanted to, you could find the breakaway by looking at where is the relative maximum value of K between 1 and 2. And you could numerically plug in some numbers and see, and it's not going to be halfway between 1 and 2. Why? Because you have these other two poles and zeros on your complex plane. But it'll be close. So now it's going to be somewhere, and I'm not even calculating it, but now you have a breakaway and you have two branches going off to infinity. They will approach the asymptotes, which is rule 4, but we didn't need that. We just wanted to know how many root locus branches exist between 1 and 2. If I ask you how many root locus branches live between 1/2 and 1, you would say 0. How many branches of the root locus live between 0 and 1/2? That would be an answer of 1. In this problem, we want to know, identify the real axis line segments where the root locus experiences a breakaway point. Now we need to sketch or apply rule 1 to put down all of our poles and zeros. There are our poles and zeros. Rule 2 now says start looking to our right on each of these segments and find an odd number of poles and zeros. There's rule 2. Now it says, are there any breakaway points? Well, there's no breakaway point here. There's no breakaway point to the left of the origin, but there are 2 branches here. Our pole 0 excess is 1, 2, 3, 4 minus 1. It's 3. So in fact, these 2 will break away, these 2 branches, and one is going to go off to this fundamental angle of 60 degrees for the asymptote. Again, this is rule 4. You didn't need to know that. All you needed to do was identify that that particular segment is where we have a breakaway point, and we have another branch symmetric to the upper branch, and it's going off at 300 degrees or minus 60 degrees. We have another branch of our diagram, root locus, going off to a 0 at infinity. We have 3 zeros at infinity. We have one going off to minus 180, one going off at 60, and one going off at minus 60 or 300 degrees. But the question here was, check all the answers that apply. We should only have one location, and that's now a z value between 1/4 and 1/2. That's where we have a breakaway. Which real axis segments belong to the root locus? Again, we quickly apply rule 1. We have a 0 at 1, we have a pole at 1/2, and we have a pole at 2. We apply rule 2. We look to the right of each of these line segments and find an odd number of poles and zeros to the right. Now you can see which real axis segments. We've split the real axis into 4 pieces, but only 2 of those pieces belong to the root locus. So now we have a piece here, or now this is for z less than, was it at 1/2? That's one segment, and we have another segment there. Ooh, maybe that's the wrong color to use, and I'm not going to be able to erase that very effectively. We have another segment here between 1 and 2. Those are our 2 answers, and you would want to click or indicate both of those options. Assume a standard. Again, this is our standard configuration. The first thing we want to do is locate where our poles and zeros are. We have a 0 at the origin. We have a pole at minus 1/2. Again, these are the values of z that cause these factors to vanish, and we have another pole at 1.5. Let's now figure out which of these real axis segments belong to the root locus. We have a segment here. This guy is going to zip into the origin, or the finite 0 at the origin, and we have another pole going off to minus infinity. Is this system going to be stable? Well, now what you would really need to do is say, well, here's my unit circle. That's a terrible unit circle, but you can see that we have a couple of different scenarios. We have this pole entering at the triangle, and we have another pole exiting at minus 1. We now need to look at the gains at those 2 locations and hope, if we want stability, for this gain to be smaller at the triangle than it is at the box. So in this case, we would look for k, which is now z plus 1/2 over z minus 1.5 all over z. And we now look at what's happening when z is equal to 1. So we now have 1.5 and we have 1/2 all divided by 1. Or this now says that we have 1/2 of 1.5, or the minimum value of our gain, hopefully, that's at the triangle, is 0.75. The value of our gain at the box is now minus 1 plus 1/2 times minus 1 minus 1.5 all over, and this is now the magnitude of z, and the denominator a value of 1 as well. Or we now have 1/2 of 2.5. So now this is 1.25. And in fact then we do have stability between the triangle and the box. So our gain now is going to be producing a stable closed loop system for a finite range of gain values. And that would be the answer that you would be looking for if that was one of your choices. If that wasn't one of your choices, you say none of the given answers. Finally, we have determined the range of k for stability. Well, this is similar to what we just did, except now we have a single pole, not two poles and a zero. And those two poles were on either side of the zero, so we didn't have our nice little story of two poles to the right of a zero. Here we have our root locus going off to minus infinity. Again, we could identify a gain to get us to the triangle and a gain to get us to the box, and we'll have to crank up the gain enough to get us inside the unit circle, but not enough to get us outside the unit circle. Again, we want to find what's our gain at the triangle, and that's now going to be, we can't forget the scaling factor or the constant in the numerator of 5. This is now going to be when z is equal to 1, or we now have 1/2 divided by 5, or k triangle is 1/10. K box is now going to be determined when z is equal to minus 1, or now we have 2.5 with the magnitude divided by 5, or now k box is equal to 0.5. We now know that our range of stability for this system is going to be bounded between a value of 0.1 and 0.5. And that all was determined by sketching our root locus, realizing that we need to crank up the gain a little bit to get us inside the unit circle, but not too much to get us outside the unit circle. Any k between 0.1 and 0.5 will in fact allow us to be having our single closed loop pole living inside the unit circle, and that's then how we would answer this particular question. I hope that now provides you with a little bit better insight into these problems like this for the Unit 6 quiz, attempt number 2.